Okay, so in this example, we have a quad geometry where there are two plates, one at the bottom, other at the top. The plate at the bottom is stationary, it is not moving. However, the top plate is moving with a velocity 3 meters per second to the right, and this is a little bit different from usual examples that you see. In the sense that in usual examples you only have a single fluid between the plates, but in this example there are two different fluids, fluid 1 and fluid 2, of different thickness, as well as different viscosities and different specific gravities which are given in the problem. And these fluids are immiscible, so there is a sharp interface between the two. And since we are moving the upper plate, there is a velocity profile in the fluid 1, and similarly there is a different velocity profile in fluid 2, but both of these velocity profiles are linear because it is a co-ed flow, uh, and the velocity of this interface between fluid 1 and fluid 2 is given, it is 2 meters per second. So in this problem we are asked to determine the ratio of the shear stress on the top plate to the shear stress on the bottom plate. Um, and now let's go ahead with finding out what that ratio is. Even though all the values of viscosities and specific gravities and these thicknesses are given here, it is uh, useful to still represent them in terms of variables so that we can do all the analysis and get a final expression. And finally, we will just then substitute the values of these variables in the final expression to find out the answer. So I'll sketch this situation again. So we have a top wall which is moving with velocity, let's say capital V. The bottom wall is not moving, it is stationary. This is the interface between fluid 1 at the top, fluid 2 at the bottom, and let's say this is the kinematic viscosity, specific gravity. Let's say the kinematic viscosity is of the top fluid is nu1, specific gravity is sg1, and similarly for the fluid 2 it is nu2 and specific gravity is sg2, and this thickness is h1 and the thickness for the second fluid is h2. Well, this is h1, this is h2, and the velocity profile is given. It is linear. In both the cases. Well, the velocity here is 0. The velocity here is 3 meters per second, which is equal to v. And the velocity here is 2 meters per second, which is, let's say, is capital U. So you already know that shear stress, the y-axis, let's say my coordinate system is such that the horizontal axis is x, vertical axis is y, is the dynamic viscosity times the velocity gradient du by dy. But again, in this problem, we are given the kinematic viscosity, and kinematic viscosity is nothing but the ratio of dynamic viscosity and the density. So this is the shear stress on the fluid. So the shear stress on the plates is equal to negative of the shear stress on the fluid. So it will be minus mu times du by dy. And since so u here is the x velocity of the fluid, which is a function of y. So since the velocity profile is linear, du by dy is easy to calculate, and du by dy is simply the difference in the u velocity divided by difference in the y coordinate. So let's say in fluid 1, du by dy will be the difference between the velocity of the top plate and the velocity at the interface divided by the thickness of this first fluid film. And in the second fluid, the gradient du by dy will be difference between the velocity of this interface and velocity of the bottom plate divided by the thickness of this fluid, which is H2. So tau yx acting on the bottom plate is basically equal to minus tau yx acting on the fluid at y equal to 0, which will be equal to minus mu2 times delta u2 divided by delta y2. So this is the expression for the shear stress acting on the bottom plate due to the fluid. And similarly, the shear stress acting on the top plate will be equal to negative of the shear stress acting on the fluid, but at y equal to h1 plus h2. So it is basically equal to negative times minus mu1 delta u1 divided by delta y2. Again, remember delta y1, delta y2 and delta y1 here are the thicknesses of these films, and delta u2 and delta u1 are basically the difference in the velocity at the top and the interface for the fluid 1, and delta u2 is the difference between the velocity of this interface and the bottom wall for the fluid 2. So if we take the ratio of these two, so tau yx on top plate divided by tau yx, that is the shear stress on the bottom plate, is simply equal to the ratio of these two, and which comes out to be mu1 divided by mu2 times delta u1 divided by delta u2 delta y2 divided by delta y1. So delta y2 is h2 and delta y1 is h1. So substituting it here, it is mu1 divided by mu2 delta u1 divided by delta u2 h2 divided by h1. Now here you can see we have dynamic viscosity in the ratio here, but what we are given in the problem is the is this kinematic viscosity. So we need to replace this dynamic viscosity uh, in terms of kinematic viscosity. And as you may know, kinematic viscosity is defined as dynamic viscosity divided by the density. And here we are given the specific densities. So it will be dynamic viscosity divided by specific gravity times the density of water. So if we rearrange the terms, the dynamic viscosity is kinematic viscosity times specific gravity times density of water. And now, as you can see, all the terms, all the terms on the right hand side are known. And so for fluid 1, mu1 is kinematic viscosity of fluid 1 times the specific gravity of fluid 1 multiplied by the density of water. Similarly, mu2 is kinematic viscosity for fluid 2, specific gravity for fluid 2, the density of water. So just substitute these here in the ratio, and what you will find out is that tau yx on the top plate divided by tau yx on the bottom plate is nothing but the ratio of specific gravities, the ratio of kinematic viscosities, and the ratio of change in the velocities, and the ratio of fluid film thickness as H2 and H1. Now delta U1 is basically delta U1 sorry, delta U1 is the difference in the velocity of top plate and the interface. So if I write it, delta U1 is basically 3 minus 2 equal to 1 meter per second, and delta U2 is the difference between this interface, the velocity of this interface, and the velocity of bottom plate, which is equal to 2 minus 0, which is 2 meters per second. Now, this is because we have no slip boundary condition, so the fluid near the top plate moves with the same velocity as that of the top plate, and the fluid and this interface, the fluid at this interface, the fluid 1 and fluid 2 again moves with the same velocity 2, which is given, and the fluid at the bottom plate is is stationary because this bottom plate is not moving. So yes, so now we also know what delta U1 and delta U2 are. So delta U1 is 1 meter per second, delta U2 is 2 meter per second, H2 and H1 are also given. H2 is 0.36 meter, H1 is 0.01 meters, SG1 and SG2 are also given, which is SG1 is 0.8, SG2 is 1.1. Kinematic viscosities are given, mu1 is 1 centistokes, mu2 is 1.3 centistokes, and yes, so just substitute these in the ratio, and what you will find out is that tau yx in the top plate divided by tau yx on the bottom plate is equal to 0.8 divided by 1.1 to 1 divided by 1.3 to 1 divided by 2 to 0.36 divided by 0.01. And now finally, we solve this, it is exactly equal to 1. So what that means is the shear stress acting on the top and the bottom plate are exactly the same. So what that means is basically the shear stress across this interface is also a constant. And because we have a linear velocity profile, the shear stress in the entire fluid one is the same, and similarly the fluid stress in the entire fluid two is the same. And because of the continuity of shear stress across a liquid interface, the shear stress acting in fluid 1 is exactly equal to the shear stress acting in fluid 2, and which is also the shear stress acting on the top and the bottom plate. So that is the reason this ratio is coming out to be 1. And this is one of the important boundary conditions to use at any fluid-fluid interface. One is the no-slip boundary condition. That means both fluids move with the same velocity. And the second is continuity of shear stress, viscous shear stress. That means tau yx across an interface. So tau yx for fluid 1 at the interface is equal to the shear stress tau yx for fluid 2 at the interface. So that's it. That's the solution to the problem.